my college at Jesus College there. I knew that Shoucheng would ask me about the history. I prepared a little. I thought that was enough. It turned out that night I learned a lot of T. Lawrence, the history from Shoucheng. And that was awkward. Then I showed him the college library, which has a very old books. That's a few hundred years old. He actually took out Aristotle's work as Aristotle's Onomy, the opera. So, and then he asked me to explain it to him. I noticed that one column is Greek, the other column is Latin. I knew nothing about it. And in the end, I learned a few Latin words from Shoucheng. All right, so, but when I learned the topological physics, that was about 10 years ago, starting from here, when the three-dimensional topological insulator was proposed. And over the years, then the progress of topological quantum materials there was a lot of progress over the years. So this was the very first one. We collaborate, and yesterday I talked about the first data I showed him, the crappy one within only 2 weeks before the sample was grown, right? Only after the sample, 2 weeks, before the sample was grown. Sorry, it's 2 weeks. So it was 2 weeks to grow the sample and took the first measurement. Although the data looks now is pretty crappy, we convinced ourselves, we agree with the calculation. And this both, and then we justify why it's different from the bismuth. And this both hypothesis turned out to be true. And then, okay. So, and then only a month later, we got the pretty nice data from the bismuth telluride and later on bismuth selenide. This is the first two three-dimensional topological insulator we measured and got the band structure, which clearly show the in-gap topological surface state. And then these are the first two works we collaborate with Shoucheng. That was a very good memory, and of course, then other collaborators we include Jimmy Analytics now at Berkeley, and Jinghao Chu now at U Washington, and Xiaolan Qi, who is present. Okay, now after the topological surface state was observed, and I trusted that. I remember there was this Tuesday colloquium from the physics department. I'm not sure it's still Tuesday or not. Shoucheng explained the topological insulator, and he said the topological surface state were robust against contaminations on the surface. Bob, I think is here. Bob, and you asked this question. And what if the surface is destroyed? Whether the topological surface state was still there. And then as a surface scientist, I myself, I had the same question. And what if I oxidize the surface? Shouldn't be the surface state just disappear? So I was thinking how to check experimentally. And then we put that into practice. And first, we tried to screw up, dope the system. And then the first thing we did was just to ask the Jimmy Analytics to dope the impurities into the bulk. And then, well, that's not exactly screwing up the surface, but well, we introduce a lot of dirt in the bulk, and that will also have dirt on the surface. So we checked that, well, the doping was effective because you see the Fermi level change a lot. However, the Dirac point was robust, and then the surface state was still there. So it seems that it's good. But then the question comes, this is a bulk doping, right? So what about the surface state? So we try to screw up the surface state by whatever the atmosphere or the gas we have in the chamber. We just dump all those things onto the surface and see what is going on. And then I will use the oxygen as an example. Then oxygen go onto the surface and oxidize the surface. What will happen? Right? And you see that the oxygen indeed went to the surface because the oxygen peak grow from nothing, right? And we can see that this is a band structure, and this part is a zooming of the 0 to 0.5 eV, this region, to clearly see the surface state. And we see that the bulk state was gradually smeared out, but the surface state remains. However, the chemical potential goes down. That means the oxygen is sucking out all the electrons. That's normal. And here is the cartoon. You can see that the chem potential keep lower up than just the more and more p doping, but the surface state dispersion persists. So if we put some potassium on the top, and then the chem potential will raise again, and then we'll see the surface state band. And you cannot do this to the bulk band. It's not reversible. So that means the surface state is stronger, the more robust than the bulk band. Well, and then of course, if we break the time reversal symmetry, and then the surface state becomes vulnerable, and the degeneracy of the Dirac point no longer holds, and then that's what we observed. We put a lot of iron into the system and saw that the Dirac point, and then now show up a dent. This is indicating the opening of a small gap. And then if we tune the chem potential into this tiny gap, we realize this massive insulating massive Dirac fermion state that can be used to realize all these exotic phenomena proposed by Shoucheng and theorists in the field. And over the years, we have a lot of collaboration thanks to the collaborators around. And there's about half still here. We thought we were pretty happy. And then one day we talked to Shoucheng, and we said what to do next. And he was mumbling and say, now you guys see so many, the evidence of the topological insulator, there's no doubt. But what the science really do, the society, is that you can make use of it. Then try what you can think of to use the topological insulator. So we thought about it. And then one of the application we thought might be possible is to use it as a flexible, transparent electrode. And here's the logic. We know this is the Dirac dispersion of, for example, like graphene. There's a spin degenerate, and then the graphene is a very good the light absorber, because no matter what's the energy of the photon coming in, even down to 0, you can always absorb it, right? But in the helical Dirac surface state in the topological insulator, although the dispersion looks similar, but there's a fundamental difference, because this two state bands has opposite spin. So if you try to excite the downspin to the upspin channel here, it's pretty hard, if not impossible. Right? Well, there's a spin after coupling. There will be small chance to jump up, but it's greatly suppressed. So try to making use of this idea. Then we talked to Yichui and Hailin Pan. Now he's in Peking University. He was the postdoc of Yichui back then. So Yichui was capable of making everything to the nanoscale. So they were able to grow the topological insulator, in this case, the bismuth selenide, the nano thick film, and it's about 10 nanometer on a transparent substrate. And we measure the transparency, and it turns out it's pretty good for the film. In the so the film in the so it's not lighting. Okay, great. So you can see that the transparency in the IR region is much better than the thing we use now is Indian dope, the zinc oxide, right? ITO. Now, each of us has a cell phone, and this is the thing, the transparent electrode on the top. However, in the visible range, then the transmission is low because this bismuth telluride is small band gap semiconductor. This is beyond its bulk band gap. This is understandable, and then we can improve that by making the bismuth selenide, the thin film, into the grid. And then in this case, in the whole spectrum range, then it achieves very high transparency. And then what is this oscillation? This oscillation actually tells us that the thickness of the film is very homogeneous. This is interference from the reflection from the top and bottom surface. This helps us to determine the thickness. That's why we know it's 10 nanometer. All right, this is one example. And later on, then, well, let me show you this test. And then in the paper, and then there's one referee says if you want to use it, you need to demonstrate it's not only reliable, but there's a repeatability, reliability. So he forced us to do some of this bending test. Here is one example. You see it's conducting, and so we can try to bend it. Yeah, I fast forward a little bit. I couldn't do that fast. And then we measure it, and then it was still conducting. And during that week, and we make an instrument to bend this thing 1,000 times to show that there's a degradation of the conduction was minimal. And it turns out after about 5 years, and we knew that the referee was Qi Kun Xue. Yeah. And then, then Yitui and Hailing and later on Zhang, they make a lot of this nano ribbon, nano wire, nano plate to make a device on topological insulator, and then realize the ambipolar gating field effect of this material. So we hope that in one day, the topological insulator, this device can be put into real use. And after working on the topological insulators, then I asked myself, now that the one-dimensional Dirac fermion is realized, it's a quantum spin Hall insulator, and two-dimensional Dirac fermion were realized too. That's graphene, or in the surface of the three-dimensional topological insulator. So what happens whether we can find a three-dimensional Dirac fermion? But the three-dimensional Dirac fermion is a four-dimensional surface that I cannot visualize. I tried to plot it, use a color as the fourth dimension, but it doesn't look like a conical shape at all. It looks like a yolk of an egg. So, but then I remember that the mathematician told us, if you project this thing into the lower dimensional subspace, linearly independent one, you can project two linearly independent subspace and prove that they're conical shape. Then you show that it's indeed a three-dimensional Dirac fermion in four-dimensional space. So we did that. And that's on the first one is on the sodium bismuth, and in collaboration with Xi Dai and Zhong Fan from IOP, China Chemical Science. And we map out a three-dimensional Fermi surface. Typically, in APAS you saw, we only show the two-dimensional Fermi surface map. Three-dimensional Fermi surface map is much more time-consuming and harder to do. But in this case, we have to do it because the two Dirac points is actually separate in the z direction. If you project it into the two-dimensional Fermi surface, you only see one. Then you miss the information. And we project the band structure to the KSKY in energy subspace, and then we measure that and then see, well, it's a Dirac point, it's conical dispersion, and that's good. And then we project it again to the KY, KZ energy subspace, which is orthogonal to the previous one. And we again saw there's a linear dispersion, but it doesn't exactly look like the conical shape here. It turns out it's a squeezed cone. Then you can see it's like this. And then the squeezed cone means that the Fermi velocity along the two ridges are different. And then this direction, where the Fermi velocity is smaller, is actually a z direction. And if you take a look at this crystal structure, this is a quasi-layered material. The electron, if we want to travel along the z direction, is harder than the in-plane directions. Right, then we prove that then we can find the three-dimensional Dirac fermion, and that's not the end of the story, of course. And if you break additional symmetry, and then a Dirac point can be split into a pair of Weyl point, well, by either breaking the inversion symmetry or the time reversal symmetry. 2011, there was proposals for the TR breaking the Weyl semi-metal, and one from Shanghai, one from the Nanjing University, and of UC Davis, and the other ones from IOP, as you guys see dice people. And we work on both systems for a while until now. Yeah, we couldn't convince ourselves. They show all these properties, except like the topological surface state and surface Fermi arcs. And about 3 or 4 years ago, that there was another family of material proposed that break the inversion symmetry. Then we jumped into those and found that indeed we were able to see that the dispersion of the Weyl fermion, and then you can see that there's almost a linear dispersion. This is a bulk band, and but at the tip of the dispersion is no longer a single point. It's an M shape, and then there's a 2 Weyl points separated. Right, a little bit. And then, of course, then the 2 Weyl point has to be connected by the surface Fermi arcs, and that's what we did. And then we locate the location of the bulk Weyl points, and then we change the photon energy, etc., to basically to change the experiment condition so that the surface state signal will excel. Then we were able to see the surface state Fermi surface, and then you can see there are 3 pieces of Fermi surface up here and the 2 pieces down here, and the 1 piece, the green one, is the surface Fermi arc that terminated at these 2 points. So then we prove that there are Weyl points. So this material, that's a tantalum arsenic, is the topological Weyl semi-metal. And of course, then we can study how to separate the Weyl points, and that's essentially determined by the strength of the spin optical coupling. This is the whole family of material. We can see the separation increase when the spin optical coupling increase from niobium phosphate to tantalum phosphate to the tantalum arsenic. Well, later on, there's a second. The second type of the topological Weyl semi-metal basically tilt the Weyl cones, and then we were able to demonstrate the spin structure of this surface Fermi arcs. And well, this families of material, we got it from the wizard, the Heusler with the Claudia Fesser's group. And we were told also that topological Weyl semi-metal, the surface Fermi arcs, have to connect it to the Weyl points. And but it doesn't tell you how to connect. So we were thinking about if we modify the surface, whether we can reconnect all this surface Fermi arc. And here's what we did. If we decorate the surface carefully, and then we were able to manipulate the Fermi arc, you can see this is a spoon-shaped Fermi arc become a very figure 8 type of Fermi arcs. So this shows the topological nature of the surface Fermi arcs. Okay, finally, we still don't remember the time reversal symmetry broken Weyl semi-metal. Why we're so obsessed to do this? Because in this case, then you can realize the simplest Weyl semi-metal with only 2 Weyl points. And the inversion symmetry broken one, you at least have 4. And then there are a lot of other states adjacent to the magnetic Weyl semi-metal that's interesting. So that's what we do. And there's recently a good hint on the candidate. It's a cobalt tin sulfide, observed the anomalous Hall effect. Then we thought that was a good one, and the calculation does show there are 6 Weyl points here. And we use our old technique. Then we measure the band structure, bulk band structure first to locate the Weyl point here, and then we also identify the surface Fermi arc that connects these Weyl points. Then we think then we show this guy can be the time reversal symmetry broken Weyl semi-metal. So I think I'll skip this part of the topological superconductors. Basically, we found this candidate in the Heusler compounds. Then this the rubidium platinum bismuth and yttrium platinum bismuth. So we show that they host the topological surface state, even though the topological surface state is buried underneath inside the bulk state, so it has a strong hybridization, yet the robustness of the surface state may be stronger than we thought. So, and then in the last few minutes, 2 or 3 minutes, then I would like to share some of the new things Shoucheng and I started a year ago. So that was about 2017. 2017 I mentioned yesterday. So we identified Shanghai as a new hub for the topological physics study, and because then there are already now a lot of the user facility, like a synchrotron, like this interconnected UHV system, like this ultra high power laser system, and as we are speaking now, they're building this Shanghai high repetition rate X-ray free electron laser. That is the counterpart of the LCLS2 here at Stanford. So we thought this is a good place, and to study the topological material and study the potential application, then we determined that we need to have a UHV interconnected cluster so that we can prepare and make the sample and fabricate the device and do the characterization all in the UHV system, so that that's free from contamination. And well, that's about that's the August of the 2018. Then we were discussing how to do the floor plan for the lab and for the offices in Shanghai back then. And we managed, we also successfully hold the first workshop for topological quantum information associated with the topological physics lab in Shanghai. So in November, yeah, you can see November 19 to 20, 2018. So unfortunately, Shoucheng's health was already deteriorated, so he was not able to attend. But after the meeting, he sent his greeting, said it was for the workshop. And some of the speakers, I think, is also present, invited speakers. Although Shoucheng started it, and he was not able to see its completion and the function, and I think we now have a very concrete plan how to proceed with this lab and how to work on the science we thought we need to do. And finally, I thank you, and of course I appreciate Shoucheng's help with me.
Question?
So you mentioned using topological insulators as transparent conductors.
Yeah.
Are the surface states really different from a sheet of graphene? Graphene famously has frequency-dependent conductivity over some region of energy.
Yeah.
Shouldn't that be true in this system as well, in a simple model?
So from the experiment, see here, then from the real usable wavelength, it seems that it's very transparent here. It's good for the use. And then this wavelength. Yeah, 1500 nanometer. Yeah, here is infrared already. Right.
What energy?
Ah.
Asking for a translation.
So I think this is 1.5 or something EV. Okay. Right, and that's a green light or blue light. I forgot. Yeah, sorry, this part.
532 is green.
Yeah, 530, here is green, right? So here is a bit blue already. So this is 3000 is far infrared already. So this is for infrared goggles things.
Yeah, I guess. Dirac, if graphene is an ideal Dirac sheet, I don't remember, but transmission loss is 2% per layer or something.
Yeah.
Perhaps your approach
So, and in this case, it's pretty thick. So if there's one layer graphene, then there's a practical problem. And one of the advantages of this system compared to graphene is that to prepare the large sheet of single crystal graphene and actually require very high temperature, 800 to 1,000 degrees Celsius. So that's not compatible with the OLED. So this guy, the growth temperature is 280 degrees. That's compatible. So that's it's good for the flexible transparent electrode. And to be honest, Shoucheng wanted us to, Yulin and me, to put this to practice. And he said he has this VC can fund us. But back then, 2012, both of us are struggling to get our tenure. So it was a pity. But well, if anyone is interested, we can still do this. And you can see here, this 10 nanometer thick sheet is very flexible. Even if you fold it by 180 degrees, then it doesn't hurt the material.
Well, to follow up, this also, I imagine this is different from graphene because you still have bulk carriers, right? It's not just the Dirac carrier.
Yeah. This, if you tune the system carefully, the bulk carrier is already.
But in that measurement, is it the case where the bulk carrier is?
So in this measurement, we already tuned this into the gap.
Yeah. But
right.
But like the frequency of the light is pretty big.
So from here, it's larger than the gap size. That's why the film, then the transmission is low. So we make it a grid shape to increase the transmission.
I see. I have another question. So you show this Weyl semimetal, and then there's different things related to Weyl semimetal. One of them is chiral spin liquid. What is that connection? Just curious, what the relation to chiral spin liquid that is? So
I think this one, I suggest you to check our literature there. So I think this axion insulator is pretty straightforward, right? And quantum normal solid insulator, conductive domain is fine.
Okay.
Yeah, I have to admit that I need to check. You got me.
Yeah. Okay. Next. Yeah.
For the magnetic wire semimetal, so what's the pattern of the spin moment, the Kagome lattice one?
It's Z direction, out of plane.
Out of plane.
So this is like a David star shape of the copper cobalt atoms that provide that magnetic.
Any other question? Okay, if there's no question, let's thank our speaker again.